Yes.
So,
I was preparing some slides, almost in the same slides that I presented before. Then there is not too much new in that slides, but in particular, I wanted to discuss the idea of duality, because I think that it is important subject in our seminar, the
yes.
concept of duality, and it is important for the theory of interaction too. Then I was looking about some concepts of duality for this presentation.
Okay, I think that'd be very good, because I mean we've discussed sort of implicitly the duality in linear algebra and how that gives rise to this notion of vectors and covectors.
Yeah, I have another.
We've also been considering like how that can be expressed algebraically, as in terms of operators, and then most recently Garrett has presented this notion of duality in terms of dual Grassmann algebras that generate Clifford algebra and or geometric algebra, and so I think for me it's not immediately clear that these are the same concepts of duality, but I'm if you are ready, Eustace, let's start with your presentation, and then maybe we'll have a lot of comments and questions.
Yeah, okay. I'm going to look the presentation. Wait a moment, please. Okay, almost. Excuse me for the delay.
No problem.
Yeah, I guess.
Yes, Professor Garrett, go ahead, please.
Yeah, I still have. It keeps lowering it down.
There's a checkbox, I think, that you can say that disables auto adjustment.
Okay, I'll try.
Okay, I am ready now.
So far, I still see only your video.
Yes. Yeah.
My mic is,
No, something. Garrett, I still couldn't hear your complete sentence. No, there's no audio. Jesus, I can see your slides. It looks fine.
Okay. Maybe I can start, and I don't know if Professor Garrett is listening to us, but
yes,
okay, thanks. Then we can start. I started again with the concept of scalar field algebra, and I wanted to talk about the concept of duality since this level first. Then, with the same idea that we were speaking before, the concept of duality needs an important concept that is evaluation. Later, for vectors and forms, we need the concept of evaluation, but here I am going to speak about the concept of evaluation, taking this from some notes of Professor Osiewicz from 2005. Then here the principal concept is evaluation that is on two sets. Evaluation is one relation between these two sets and one set that are the value set. For example, reals or complex or some fields in general. Then phi is called application of duality. This phrase is taken from the same notes of Professor Osiewicz. Then here the idea is to use the concept of duality in the sets A and B that are dual sets. Then the application, the evaluation function can be interpreted in different ways. The first is like an application on the Cartesian product of A and B to the set of value set. The second is an application over A to the potence set of B. Then here the here the interpretation of this relation is taken in the way that A have one passive A is passive here, and B is the operator acting on A.
Just one comment is that in
Yes.
In mathematical logic, this is usually referred to as currying of a function. Right? So you have a function phi of 2 arguments, and from that function phi, we can use currying to this currying curry from I think it is the name of the mathematician was Curry, and he said that this can be done with any mapping that is a mapping from a product of 2 elements into a 3rd element, always gives rise to these curried equivalent higher order functions, right? Because the 2nd and 3rd definitions are mappings from, say, A into the functions B into V, right? Or B into the functions A into V. So.
Okay, and thank you very much. Can you write in the chat the word, because I
The word, yes.
understand the.
Yes. And so. So we in a 2 argument.
All right.
The main thing is that you have introduced the notion of objects into the category that are higher order, right? So that the
Okay.
you have a power function within the category that allows you to say you're interested in mappings or sets whose elements are mappings, right?
Yes.
So these are just higher order equivalent functions.
Okay, and I think that it is important because here then the function B is not in the same level of A. No? A are sets, and then the power of B is getting by the current. You use the word current?
Yes.
By the current of B into the power of V. Then in this 2 interpretation, the concept of duality is important because the level of some of age of the sets are not the same. When we think in this relation in terms of Cartesian product, what functions, what sets are in the same level? And then we have one transformation to the set of value. One morphism to the set of values. But in the next two, the interpretation is different because the domain and codomain are different in these relations. Then I think that this is an important idea that Professor Osiewicz was working, because after we can go ahead in the interpretation of phi. Phi is the function that represents the evaluation, and then we can think in this in this way. I taken again this from the notes of Professor Osiewicz. Then phi is an application of two sets, the domain and the set, the value set, and then we take two elements, one from the domain and one from the power of B, and then we can think in the evaluation in these three different forms. Then the participation of each element here can be interpreted in different forms, but those are very important because it is necessary to take both approach, because they are saying to us different things about this relation. Okay. Here, the last one is taking an X like a functional, and then this is an object of different category.
Now, Jesus, when you started, you wrote A cross B, and that you showed like after purring, you had A into V to the power B. Here, I'm wondering.
Yeah, f of x is,
Do you want I move to the
Previous, yes, just
previous? Yes, okay.
yeah. So if we take say the let me just see if I can point here. Oh no, I don't know. Doesn't want to let me do that. But the last two statements, for example, the last one is a mapping from B into V to the power A. Now on the next slide, if you just go to the next slide, now you have let's see, so V to the power D.
Here, maybe we can say that
But see this, I'm just having this small problem because I see you wrote like F comma X. Is that what do you mean by writing F comma X in parentheses?
f comma x in parentheses, or
Yeah,
without.
So you mean here a mapping? It's like given an f and given an x, then you can use phi to get
You are speaking in this row. Excuse me.
the one above.
Okay, the one, this one.
Yes. So
Okay.
you're saying given f and given x, phi gives us what?
Yes, here fx is an element of V,
A
of
v.
V,
Yeah.
of V. Then we are here in the first one of the prior expressions, that is phi acting on A cross B to B. Is the first one.
Yeah, in other words,
We lost your voice, Professor Garrett.
But f is a power, right? From, is it not? It's an element of a power set of a
in the second, X is element of D, and F is an element of, excuse me, no, so clear. F is an element of B to D.
the D. Yes, but also in the first case, right?
But in the first case, if we think like domain, the Cartesian product, then it is different, because it's one application on the Cartesian product to the set B. And in the last one, this, okay, here of delta is one element of BD, and F is an element of D. So, no, sorry, I'm going to write here. This is an element of B to D, and F is an element of D. This is here. At the end, this is one element of the set B at the end.
I'm still having trouble. Like, first the first line has an arrow pointing to what looks like an equivalence, like a symbol.
Oh, there's an
Typo?
error. Yes, this is out of.
Oh,
Yeah,
Excuse
so-
Now, FX just means the domain of F, I guess. You're mapping with your application to the domain of F. That's all you're saying, I think, right?
We are mapping the application to the domain of F. You are thinking in the first line?
Yes.
Sorry, I'm going to erase again because there are many things here.
So to me, my my intuition is that this first line is related to the second line of the previous slide, so that first line is for a given F, and F is an element of the power set V to the D, and given an X, which is an element of D, then we can apply that F to X, right?
Maybe I'm going to move here, and we can take the first line. Then if I have X, I have the first line. If I have a F element of A and X element of B, okay, this is for all the no, excuse me, for the first line only. Then I have the mapping phi on F, comma X to Fx. No, parenthesis is not here. Fx. And it is defined like Fx.
Yes.
Yes. Okay. This is the first line. Then we are taking elements of both sets, and then A is equivalent here to no. Sorry. Fx are element of A plus B. And this is the domain. This is the domain here. And even I have here a relation between the domain and the values. This is in general that those I am working now. Then in the first line, this is the meaning.
But if we write F applied to X, then I don't know, F is of a different kind of thing than B, right? Than X, right? So that
Okay.
F is a function and X is a value on which the function operates.
in the second.
No, in the first, the first one, you said F is an element of A, but then later in the same line, you wrote that this mapping is equivalent to F of X.
Okay, but this
So
is
how do we understand applying an element of A onto an element of B?
okay. This is the central part of the discussion of this presentation that Professor Osiewicz made. The idea is that Fx can be interpreted like Fx when where F is fixed and X is can have different values. But this can be interpreted here, X on F, maybe in this way. The same Fx can be interpreted in this way. His ideas was that the concepts of variable dependent and independent was wrong, because both elements here are in the same level. Maybe we can put the excuse me, I am trying to not here, then
So I just tried to write here in the chat window what I think is a way to express
okay.
evaluation, right? So that if we write F is in V of A, right?
Okay.
And then we can write we can write the evaluation of F on X, for example, and it means the same thing as F of X. Right?
Okay.
So that first line is V to the power A cross A. Right? So that means that that says that if we have a higher order object like V to the A, and we have an A, then we know how to apply the element of VA to A. Right.
Okay, but this is sorry.
Is it's different than what you wrote in your original slide?
Yes, because I understand this that you write in the chat, like the second row in the slide. I'm going to put again the slide. And
Yes.
the second row is this. Yes. Mhm.
But the last line, for example, says that if I know an element of B, then phi can give me an element of the power set,
Of
A
the power.
into V.
Yes.
So
But,
so we would write so we would write, say, phi of B gives me a function which then we can then apply to an A.
to here.
Yes.
Okay. Mhm.
So
Yes.
so then we would say phi of B applied to A. So we would write phi of B, and then in another set of parentheses.
Okay. Applied to A.
Yeah, which is
Applied
then B. Right.
And then only B here. Yes.
Yes.
Okay. Only B. Mhm. Yes. This is this arrow. No?
Well, the first arrow on that last line, is the mapping that takes you from B into functions on A into V. Right?
I did not understand if you are. I'm going to erase this. I can put again, but if I put only until this this point, I think maybe there is not problem.
I think I understand this slide is clear to me, but the next slide I am confused.
Okay. Okay. Here.
Yes, because you write F is an element of VD, so I wrote VA, for example, V to the power A, and X is an element of D. So what you just write here is like what I call the evaluation in my chat window.
Oh, okay. Okay. Then here, F is an element of B to D. The domain, the power of the domain. Yes. Okay. Then here in the first row, we have okay, I see the problem because this is X. Okay. Okay, then the problem is this this. Because if I wanted to be consistent with the prior slide, then I need to move this. And here, F is element of F, or no, excuse me, no. Here, F X are elements of the domain, no? And F X is an element of V in the first row, in this row. And here, we need to, is F applying on X, then F is an element of B to D, and X is an element of the domain. This is here. And here, F is an element of the domain, and this is an element of the B to D. Because it's only the application of the definitions of the prior slide.
Okay, with the last one, I think I understand as being one of the curried versions of phi, right?
Yes.
So you take the domain D, and then you get functions D into V.
Yes. Yes.
The first one, the one before that, okay, you take okay, well, I'm
No. Okay, maybe I think that it is necessary to review this with more careful. Then I'm going to do that.
okay.
But,
I think that the last two lines I understand quite well, and I think I understand how it relates to the first slide. The first line, though, I'm not so clear.
Okay.
Like when you write F comma X, I'm
Yes. Because here the domain is
So that's really the standard definition of duality, is it not the first one?
the first one is the standard definition of duality. Excuse me, Professor Garrett.
Yes, that's what I understand. The first line is just the usual definition of duality. You know, that F maps X into the value space, the value set. So that's standard definition what we mean by a functional F, as I understand it.
Or yes, I mean it is an application, right? It says
Yes,
we apply-
yes.
It's functional, mapping the domain into scalars, real numbers or whatever they are.
Yes. This is okay. We can say this is a standard definition of duality. But these have different interpretations, because here there is a mapping from the cross, excuse me, the Cartesian product to the value is the first one. And in the next two, the domain and codomain are different but there are the same, they are based on the same definition.
Mhm.
And
And the third one,
yes,
yeah, I'm trying to understand the third one. It looks like the second one is just for a fixed functional, you're mapping it into
yes.
the domain of F, I guess.
And the third one is the delta de Dirac applied to F.
Okay.
Could you write, say, integral of x, right? So as a functional, right?
It's a functional, yes. Mhm.
Yeah, so that the functional is applied to a function to get a
Okay.
value,
Exactly. Mhm.
Mhm. Yes.
whereas the other one is a function is applied to a value to get a value.
Okay, maybe it's clear now.
Okay. Yeah. Maybe I can go to the next.
Okay.
Yes,
Yes. Okay. Then, okay, here is some slides that we were that were presented the past, but I wanted to maintain here because is the principal definition in the of the Grassmann algebra. Then nothing new here, but only the idea is that the first two are the definition of multivectors that are defined on V, no? And the next two are the definition of multiform that are in the dual of V. Then again, we have here the duality concept.
Now you have
And-
two Grassmann algebras, one of them to do, so that's like what I was doing then. Something like it anyway.
Yes, then we have here two Grassmann algebras. One of in the vector forms, and the other one in the multiforms.
and you will say that the duality implies that there's an evaluation that relates the two, right?
Yes, yes. then when we defined these algebras, then we are now thinking about one pair of Grassmann algebras. And these parts of Grassmann algebras are used in the evaluation. Excuse me, Garrett, we lost you.
Yeah, there's no definition of a Clifford algebra in terms of the two Grassmann algebras, the dual, the Grassmann algebra and its dual Grassmann algebra. My internet's still bad, I guess, right? It's not very good.
Sometimes it's okay, and then other times the words are distorted,
Garbled.
garbled. Yes.
Yeah, that's AT&T. That's you know.
If one thing that might help is that if you can still hear us, if you reduce your volume.
Turn off my video.
Well, the video
Maybe if I
might help. That might help, but also
Yeah, okay.
it sounds to me like the sound of your voice is interfering.
Okay,
with.
yeah, I turned it down. Is that better?
Yes,
No,
that
I
sounds
turned
good.
down my volume.
Yes, that sounds better.
No, that turned on. Yeah, it turned it.
It was better,
Is that
but
any better?
maybe. Sometimes it's okay, and sometimes not.
Okay, well, yeah. I might try another internet, I guess.
I always have better results with earphones, like without having the speaker. Sometimes the speaker on your computer interferes with the microphone, so that.
Okay.
So I generally use earphones, but I use the speaker in my computer, but I use the microphone in my computer, but not the speaker. The sound comes directly to my ears, so that avoids having the sound feed back into the microphone.
Okay, let me see if I can find earphones. Just a second.
Yes. This evaluation map that you show here uses.
Yes.
It looks clear to me, I think. But I guess what I have some difficulty is seeing in this evaluation map the product that you showed on the first slide, like A cross B. I don't see here A cross B anymore, right?
Okay, but here maybe we go to here, I have here the
Yes,
gross product. But okay, in this in the prior slide, the problem is that we have here one maybe we need to define one functor from the first maybe I try to write something here from here but here to here then with this I need one category of that is on B or BF. And here I have one that is in the dual.
V star, yeah.
Yeah. And then we need one functor from here from BF cross BF to the reals. Yeah, I think that this is, but then is necessary to elaborate another map for showing this.
Yes, I think that's clear to me. Garrett, are you?
Yeah, I did. Is that any better now? I did. I am using earphones now. Is that better?
Yes, it's better.
Yes, yes, it seems fine.
Okay, so maybe that was the problem. It was just feeding back or something like that. So I will keep using earphones. Sorry
Okay.
for the trouble.
Oh, no problem at all.
Then
so now we have vectors and forms on this slide, vectors and covectors.
yes, and those are
So a form is a covector, then DF is a covector, really.
yes. DF is a covector, and here is a vector.
Okay, partial derivative is a vector then.
It's a vector, a covector.
Okay.
Then in this we have again the duality principle, but both of them are used in the evaluation. Then again we have here the evaluation that is the way that we use both vectors and covectors or multivectors and multiforms in this description.
So this relationship, I'm not sure I see that in what Garrett like what you wrote, Dr. Sobczak, in your paper on duality. So you had two Grassmann algebras, and you could write an element of one Grassmann algebra with times the element of a second Grassmann algebra as a like, so if A came from one Grassmann algebra and B came from the other Grassmann algebra, you considered an algebra in which there are products A, B. So it looks something like this, but you didn't call your product A-B evaluation, right?
Well, that's right. Yeah, I was actually defining what I mean by duality is really a different, it's taking a dual, or first of all, I defined duality to be that simple relationship. But of course, that's not the case here. You're really considering covectors in completely different spaces, whereas I'm putting my covectors and vectors in the same space. But they still involve two Grassmann algebras.
Well, that's why when I first looked at your paper, I was a little bit confused as to where the product AB exists. Like, so that I know that A and say, if I have two elements of the first Grassmann algebra, I can take their product and it's the Grassmann product. That's within a single Grassmann algebra. But when I take the second Grassmann algebra, I can do the same thing there. But as soon as I mix the elements, from one Grassmann algebra with the other Grassmann algebra, then the products are no longer in either of those Grassmann algebras, right? They're in something else. They're elements. They're elements of the Clifford algebra, right?
Yeah, the standard way of looking at things. That's where this idea of the so-called mother Clifford algebra comes from, where you have a Clifford algebra of signature n, where you have as many vectors with square plus 1 and square minus 1. And that gives you a structure of a matrix, really. It's linear algebra, really. It's just another way of looking at a linear function. Matrix, really. But that's right. It just doesn't really fit into the standard way of looking at a space, a vector space, and vector space of covectors. It's always a mapping to real numbers, whereas it's just, it seems to be just different, really. But I think that's what stumbles, why people don't accept Clifford algebra more widely, because they think about it in different ways. And what I'm thinking about is the generalization of the real numbers to include the idea of bivectors, trivectors, and so on, whereas most people don't look at it that way. Well, differential forms is, of course, they introduce all kinds of machinery onto differential forms, like double dual, the Hodge duality, and different ways of getting the same structure as a Clifford algebra, but not using Clifford algebra. You can raise a differential form 1 degree, but you can also lower by taking the contraction operator. So that really corresponds to operations in the Clifford algebra.
Well, here this evaluation is equivalent to contraction.
Exactly.
Yes. Right, so we take the tensor product of a vector and a form, and then we do a contraction. Right?
I was trying to find one relation between this formulation and the Clifford algebra formulation. I didn't get too much. But in Dedekind book, he speak about one important thing that I think can be important in these relations, because he speak about one base of the functions and a complementary base. I don't remember the notations, but maybe something like this. We can say E1, E2, etc. En about the one base of functions, and then he after speak about one complementary base that have no, excuse me, here's theta. That are in different a different way of describing the space. But he made one important concept here, because he speak about one basis of the of a module. No? And this is then a basis of a dual module. Then in this way, he can speak about this split of the space in one base using the base of module, and the dual and the base from the dual module.
Do you remember what paper that is? I think Zbyszek wrote a paper similar to that early.
And the paper is this book of Dedekind. Wait a moment, I give you the reference. Okay, a theory of algebraic functions of one variable.
Okay.
Dedekind and Weber. In fact, that was I were preparing for today. This because the concept of duality, I think that it is important in the algebra that it is for observer. Then this was the idea.
So I was trying to express just while you were looking there, I was trying to see evaluation as being somehow found in the Grassmann algebra that is derived by maybe I should say it's something like an operator in the Clifford algebra that maps say products AB. So the product AB is like where A and B come from Grassmann algebra. That's a result from Garrett's paper, right? That we can always take any element of the Clifford algebra and express it in terms of the duals. But in order to have evaluation of the kind that you've written, Jesus, there's something missing still. Like given this element of the Clifford algebra, we need to be able to evaluate it. We need to take that product, which is a product of two Grassmann algebras, and then map that product, which is an element of the Clifford algebra, into the reals or into the scalars. But maybe this exists. Like maybe there is a way in Clifford algebra to explicitly write the evaluation, right? So that I'm not sure. Is that?
Yeah, maybe it's an, you map the product B into a homomorphism of f of A times f of B or something like that.
Well, I was thinking more of something like scalar product, right? So if we have AB, which is an element of the Clifford algebra, then we can take its scalar product and we end up with a scalar, right?
Yeah, but
so then we can say given this scalar product, then we know how to evaluate A and B. We know how to evaluate A onto B. We just take its scalar
well, of course, that's what they do in differential forms. They take two R forms, for example, and map it into scalars. So I guess that's exactly what they're doing really with differential forms. They take two R vectors, map it into a scalar, or as you were saying.
Well, maybe back up a little bit. Remember, Eustace, when we wrote, for example, the tensor product of a form times a vector. So this is a two tensor, right? Or a 1-1 tensor, right? So this 1-1 tensor, or we can think of it as, perhaps we can think of those 1-1 tensors as elements of a Clifford algebra, right? So that we didn't usually consider that the 1-1 tensors form a Clifford algebra, but maybe there is a sense in which that's true. I mean, and when the same thing that happens in Garrett's paper, where we consider matrix representation of elements of the Clifford algebra, the matrix should be considered perhaps to be equivalent to a 1-1 tensor, right? So that we have rows and columns, right? So we distinguish one type of thing with one type of vector.
So what do you mean by a 1-1 tensor again? You have what? That's one covector and one vector. Is that That's what it is, right?
Well, one, if
It's
you
a
write
function
it,
of one, one
You-
tensor is one
if,
vector
if
and
you-
one covector, I suppose, mapping to the
well,
scalars. Is that
in a
correct?
sense, right? Symbolically, you would say it has one upper index and one lower index.
Oh, okay, yeah. Okay, yeah, yeah, that's another, yeah.
Um, so it's how you, when you think about matrices, you don't necessarily think of the matrix as having a distinction between rows and columns, right? You just think of it as a rectangular array. But when you think about tensors, I mean, the closest thing to a matrix in a tensor is this 1-1 type of tensor, right? Because you can take a tensor product of a 1-1 tensor and another 1-1 tensor and then do the contraction between the two, and you end up with a new 1-1 tensor. So it's like composition, right? So in the tensor algebra, you have something equivalent to composition. And so what I'm thinking maybe is that in the Clifford algebra, we can do something similar, right? So we use the Clifford algebra as the kind of mother algebra, right? Right. Like
Well,
in which,
that's exactly what I think I'm doing, actually, in my ways looking at it.
so you aren't really you aren't really making a strong distinction between matrix algebra and Clifford algebra anymore.
No, that's right. In fact, I'm saying,
You're saying basically they're the same.
yeah, a matrix is just a coordinate matrix of a element in a Clifford algebra, or many different possibilities, but matrices are basically coordinates of Clifford, of multivectors, with a geometric interpretation that goes along with it. But of course, there are many different geometric interpretations, and I'm trying to standardize that idea, actually. That's what people call the mother Clifford algebra, where you had a 1-1 Clifford algebra is a Clifford algebra with two anti-commuting basis vectors, one which has square +1 and the other which has square -1. And you can compare the ones with square
Something was garbled there, but when you write a 1-1 Clifford algebra, the term 1-1 is being used in a different way, right? So that in Clifford algebra, everything is vectors or multivectors. So it's all say upper indices, right? But they're alternating, right? So you have, in tensor notation, you'd write like T superscript A B, right? But you indicate that A and B is alternating, right? So that's but if you write T superscript A and then with a subscript B, then you're saying something rather different, right? You're
Yeah, different but the same.
but still, what I was still looking for is what is the equivalent of evaluation? Like if these two Grassmann algebras that you use to express the Clifford algebra are dual, then there should be something equivalent to evaluation. In order to justify the term dual, right? To justify that A and B are dual Grassmann algebras, then we need in some way to be able to take an element of A and apply it to an element of B, right? So that, and we can, yeah, so that's different, right?
But
see what I want to write is something like evaluate a B something like that,
Yeah.
right? And what I mean by that is A on B. Right?
Or maybe like a contraction. A contraction.
Like a contraction. So that's why I proposed that maybe eval like eval AB is equal to A dot B. Right? I mean,
Okay.
maybe.
How about this one right here? Look. That.
Because in Grassmann algebra, no, excuse me.
No, I wrote the wrong thing.
In Clifford algebra, you have defined an internal product.
Okay, let's see.
Yes. Yeah, sorry, I wrote the wrong thing initially, but what I just wrote here is that evaluation of A on B is, and so where AB is an element of the Clifford algebra, then we can take its square, for example, with respect to the scalar product. And we can say that's an element of the reals. Is that?
So that's something that, you know, the symmetric part is just the inner product, and the anti-symmetric part is mapping it onto the elements of the Grassmann algebra. Two vector, bivector. The second part's a bivector.
But those are vectors, but there are not forms.
Oh, that's right. B
Yeah,
is
they're
not
not-
really a covector. It's also a vector. That's right.
Because you want to
That's
take,
what I guess is confusing. The way people always think about a vector and a covector as completely different objects. A covector is a mapping of vectors to scalars, whereas a vector is just a vector.
Because there is one interesting theorem, I remember, that you can split the space in the product of one multivector and a form in the tensor product of one multivector and one form. The multivector depends of the base you are using, but multiforms is unique. Then if you have one space of n dimensions, and then you have one form of n minus 1 dimensions, only there are one vector that is like the time-like vectors in this theory. Then this is how can I describe a multiform with Clifford algebra? I don't know.
Well, you just take the outer product, you know, take all the scalar products equal to 0, then you have a Grassmann algebra.
No, but there are Grassmann algebra in multivectors, but those are not multiforms.
Yeah, for example, one way of duality in Clifford algebra is you let I equal to the n vector. And then you multiply I times any, and then I times a vector, I times a vector is equal to an n minus 1 vector. I is an n vector, I times a vector is an n minus 1 vector. So that's called duality. And that's the thing, duality is used in many different ways. that is not quite compatible with the usual way of looking at it, I guess. IV. And that's, of course, like taking a contraction of a form, what people usually I do with forms. So I, a pseudoscalar, an n vector times a vector is an n minus 1 vector, or I times a k vector, say, times a k vector. That's equal to a k minus 1 vector. So, you know, so that's by the idea of taking duality by multiplying by a k vector, by an n vector. An n vector is the highest degree element in the Clifford algebra generated by n orthogonal vectors or n linearly independent vectors. But you can see, you can always compare that to differential forms by taking the scalar product or contraction or however you want to look at it of a differential form. We work on those ideas quite completely in this book with Hestenes, Clifford Algebra to Geometric Algebra, Unified Language for Mathematics and Physics. In fact, yeah, that's
because I understand that you can go to different degree of multivectors with the internal product, but I insist those are not forms.
well, that's true.
When you say an n minus 1 vector, that would usually be called a pseudo vector, right?
That's right. Well, an n vector is a pseudoscalar. Okay, so the highest degree element.
So
is
there is a Hodge duality that takes
well,
you.
that's right. That's right.
It takes you from vectors
So
to pseudo vectors, or vice versa.
Yeah, there's direct relationships. People know direct relationships between differential forms and Clifford algebra. That's pretty well known, really.
But I'm not sure that pseudo vectors are a suitable way of representing covectors, right? Is that what you're?
Okay.
Or
Well, that's
you were,
right.
you were
That's where the
suggesting
confusion arises.
You said maybe the pseudo vector is, you know, the dual of a vector. So the dual of the vector would otherwise be a covector. So you're suggesting that there's some kind of relationship between covectors and pseudo vectors.
Well, yeah, that's right. Well, that's the okay. So that's equal to A dot B. I'll just write this. Okay, that's the most basic formula in Clifford algebra. You take two vectors, you multiply them together, you take the symmetric part, AB plus BA divided by 2, and the anti-symmetric part, 1/2 AB minus BA, and you identify one as the usual scalar product between vectors, and the other one is what defines a bivector. But that's not a covector, it's just a quantity. Like a vector is a one vector, two vectors is a bivector, three vectors is a trivector, and so on.
Mm-hmm.
But that's all in the vector space. The covectors are, well, in Clifford algebra, you define covectors as a dual, which is, of course, confusing because it's not quite the same thing.
But here, this is an element of multivectors form.
That's right. That's right. It's in a multivector algebra.
Multivector algebra. That was that I presented in the first definition of Grassmann algebras.
Yeah, that's right. A Grassmann algebra is just that's the same thing as a Clifford algebra with zero scalar product. And of course, that's why I use dual or null vectors A null vector is just a squared equals 0. Definition of a null vector, or nilpotent.
Sorry, I need to connect my.
Yeah, nilpotent.
To plug.
But that's
Okay.
that's the thing. If you take a vector which has square plus 1 and a vector which has square minus 1, and they're anti-commuting, then the sum of those two vectors is a nilpotent basic relationship. Okay, so that's what I write as. I can write that down. Say E plus F squared equals E squared plus EF plus FE plus F squared equals 1 minus 1 equals to 0. There you go. So I'm thinking about E and F as being a vector which has E squared is equal to 1, F squared is equal to minus 1, and EF and FE are anti-commuting. So EF plus FE is equal to 0. Well, so you get 1 plus minus 1, and of course that's 0. So that's a nilpotent. That's a basic construction. That E and F define the Clifford algebra 1, 1. Well, that's not quite the same thing, of course, as the tensor up with an upper indice and a lower. It's not, well, it's a little different. You can put them, you can identify them, but you know, a Clifford algebra really is multivectors, whereas a tensor algebra, tensors are all scalar products, really. They're all defined on the real numbers. So I hope my audio is better now. Is it still garbled?
Yeah.
Is it?
No, your audio is definitely better.
Okay, well, that's good because
Yeah, it's,
yeah. So EF then generate the Clifford algebra 1, 1, and that's isomorphic to 2 by 2 real matrices. Very simply. So, in fact, I think that's the way people should look at 2 by 2 real matrices. Is the same thing as the Clifford algebras CL 1, 1. And you see, yeah, so E is a vector which has square plus 1, F is a vector which has square minus 1. And then you can get the Pauli matrices in a very simple way by, you know, the same thing I've done in my talks. So I'm trying to emphasize the close relationship between any matrix and well, 2 by 2 matrices is a simple example, and that's what I use A and B. A plus B, or AB plus BA is equal to 1. It's the defining relationship on 2 Grossman algebras. A and B define Grossman algebras. Well, actually, they're nilpotent. So, by the way, what I've been thinking about lately is the idea of the so-called enveloping algebra of a Clifford algebra. The enveloping algebras are infinite dimensional algebras, but I'm trying to relate that now. Well, they always talk about, that's what Dr. Santilli was interested in, the enveloping Lie algebra of a Lie algebra. And it's an infinite dimensional space. Well, I'm looking at that now in terms of the corresponding ideas and generated by these nilpotents. And it's actually pretty interesting, and I'm getting some interesting results, which I'll use for this paper I'm going to give at this ICA CGA conference that will be coming up in October. I have a little time still on that. I did finish my my acknowledgement. I will send you the acknowledgement. I did acknowledge and thank our research group that we're talking about right now, you know, the Ojevich Research Group. I'll send you a copy of that, the finalized version of that paper. The only thing you don't have is the acknowledgement, which I acknowledge our group actually as being very important because it gave me opportunity of talking about these ideas.
Well, I appreciate that. I think that will be useful, and perhaps some people there at that meeting will stop by and find out what we're talking about every couple of weeks.
Well, the interesting thing is they scheduled my talk directly after David Heston's talk, which is pretty nice, actually. You know, David is being glorified in this conference. The conference is in his honor, but I'm giving a talk right after his talk.
History isn't always kind, but maybe that's as much as you can expect, right?
Well, I think that Dave has tried to basically cut me off, basically, because anyway, I don't like to talk about it really, but
yeah.
But so it'll be interesting at this conference to see how it goes. I only have 20 minutes to talk. David has a whole hour. It's the honorary invited speaker, but anyway, it doesn't matter. Yeah, it is. I think it is ridiculous that they want $150. I had to pay that myself, but it should be an interesting conference.
Yeah, I'm still wondering. I might actually show up and spend some time there, but I haven't committed myself yet.
Well, get them to give you. I noticed on their damn program they want $200 because you didn't the early bird, but I'm not an early bird, so just $150. They'll probably let you in because they let me in. I never was an early bird. I was waiting to whether they accepted my paper and so on. But anyway.
Just on the chat window there, what you wrote partway up, the expression was that you have some n vector times a k vector is equal to a k minus 1 vector. And I wanted to understand if this should be viewed like a contraction, right? You know,
yes, exactly. That's exactly what it is. In fact, you can define it into a contraction of a 2 tensor or a 1 tensor to a scalar, a covector. That's where the idea of a covector comes in.
Yes. So the sense in which this duality, in the same way that Jesus, was talking about in the early part of the presentation, this contraction is an essential part of the evaluation that Jesus was talking about. It's not evaluation in itself, because first of all, you have to be able to take the product. So you need to do the AB in order to have this. You need to have something in order to contract. In other words, right? So.
Okay, well, I wrote down another expression there. So the Clifford algebra G11 is spanned by 1, a vector squared plus 1, a vector squared minus 1, and their product. And they're assumed to be anti-commutative. Okay, so EF is equal to F minus FE. Then that's a bivector, a unit bivector. Then. And of course, you can see there's 4 elements in it, all of which are very easily represented in terms of matrices. One is the identity 2x2 matrix. And you can see, for example, if I multiply EF times F minus E. So in the Clifford algebra G11, the pseudoscalar is just E times F. That's the pseudoscalar, the highest degree Clifford algebra element. If you multiply that times F, well, F squared is equal to -1, so you get minus E then. That's the dual of F with respect to the pseudoscalar E times F, which is the
But underlying this Clifford algebra, you show that there are two Grassmann algebras, right?
That's right. That's right. One is generated by G. Okay, that's the Grassmann algebra now.
It's one in E, and the other one is one in F, I guess.
And just a second. And G star. Oh dear. Where's my star here? There it is. Oh, B, okay. So one Grassmann algebra is G1 is equal to A. Remember, A now is a null vector. A squared is equal to 0, and the dual element is B. And equals A minus B. And AB plus BA equals 1. Okay, so we have A squared equals B squared equals 0. And you can think about them as matrices if you like. A is just a matrix. A equals matrix, what, 0, 0, 1, 0. B is a matrix.
Now you are building
1.
this algebra using AB.
That's right.
Okay.
So that's a two. A is the matrix. It's a nilpotent. You can see A squared is equal to 0,
Okay,
just like
yeah.
how I define my A.
Mhm.
And B squared is equal to 0.
Mhm.
And E, well, of course, E is a matrix. A plus B. Well, okay, now you see I must.
Oops. There's something interrupted here.
We lost.
Yes, there seems to be an interruption.
Oh.
So, Mike, oops, I guess
Yeah.
perhaps you'll connect again. But my question was going to be if so we have this Grassmann algebra G and then the Grassmann algebra G star. And if we have the G stars as corresponding to covectors somehow.
Yes, maybe.
Sorry, my internet is not very good. Can you hear me again?
Yes.
Yeah.
Okay, so I'll get back to the.
Yeah. So Garrett, I was going to ask something like, the notation that you used here was G1 and G hat star. Maybe I'm not sure if that's, is that really what? Maybe I didn't understand really, but.
Yeah, so you can think about A and B as just being the matrices. The matrices. So A is 0, 0, 1, 0, and B is 0, 1. Of course, A plus B is just the matrix A plus the matrix of B, which is, of course, sigma 1, the Pauli matrix for sigma 1.
But
Right.
here, how the duality in B can be found.
Okay, well, that's the thing that's confusing, I suppose. Like in this geometric algebra, the pseudoscalar is E times F.
Okay.
Phi vector. In G11. So that's the easiest algebra. Just think about Pauli matrices. Well, okay, you don't. That's what you really have to look at. The simplest case is G11, really. And then after that, everything is constructed just by taking a tensor product or product.
Uh-oh. Everything was going okay, but then you got interrupted again. I just wanted to recall.
Chat box again. Yeah.
I wanted to recall an expression that you wrote a little bit earlier. That was the two Grassmann algebras. Like you wrote that A comes from one of the Grassmann algebras and B comes from the other Grassmann algebras. Right? Maybe that expression isn't. Maybe there's a syntactical problem. I'm not sure.
Okay, yeah, I have that on my chat box. Do you see that? I'm looking at it right now.
Yeah, I copied one line that you entered. That is that EF and F is equal to minus E, and G1 is equal A, and G hat star is equal B. Like,
That's right.
I'm not sure I understood the notation because you wrote G1. What did you mean G1?
That's the Grassmann algebra generated by one element, A.
And what did you mean by G hat star?
Well, that's a second Grassmann algebra generated by B.
So
And they satisfy AB plus BA is equal to 1.
yeah. So wouldn't that be G1 hat star?
Yeah, that's right. You could say that. Yeah, that's right. G1 star is equal to B. So that's another way of looking at duality. So that's really different. That's not the same thing as multiplying by EF. I'm just, so my duality is this expression AB plus BA is equal to 1. I call that compatible nilpotents, compatible null vectors, AB plus BA equal to 1. So basically, that's the same thing as AB plus BA in Clifford algebra. That's the same thing as 1/2 A dot B. So we're in Clifford algebra right away, you see. So AB.
But But ultimately, I want to
be-
be able to think that the Grassmann algebra G are vectors, and the Grassmann algebra G star, or maybe is covectors.
Oh, by the way, that's it. The other one, that AB plus BA is equal to 1/2, you see. Is that right? Yeah, that's correct, I think. Yeah. That's a little confusing because yeah, A dot B is equal to 1/2. Yeah. So 2 A dot B equals 1. No, what am I writing here? This is wrong. AB plus BA is equal to 1. AB plus BA is equal to 1. Okay, but that's equal to, yeah, okay. By definition, AB plus BA is equal to 2 A dot B. Okay, that's equal to 1. So A dot B is equal to 1/2. Yeah.
Okay. In any case, I think we're struggling to make the connection, but I think I can sort of see that perhaps one can treat the Clifford algebra as the algebra in which we can actually express the evaluations in order to justify the claim that the Grassmann algebras are dual, and therefore that one of the Grassmann algebras is Grassmann algebra of covectors, and the other Grassmann algebra is the algebra of vectors or multivectors.
Yeah, the whole problem is just duality is used in so many different ways. For example, the Hodge duality in differential forms and so on, that it gets very confusing to separate out the different ideas or contract differential form. It can be very confusing, unfortunately. But that's the way the history of mathematics goes.
But I think what Jesus referred to earlier was Shevich's desire to define duality in a high level way, so that whenever you use the word duality, it would always follow the same pattern. There would always be this A cross B into scalars, from which then you could then define evaluation and so forth. So you have just one notion of duality, but then you could apply it in different ways. Right?
But he doesn't mention the idea of a Clifford algebra at all. Then it's completely avoided, right? So
well, the Clifford algebra, what takes the place of the Clifford algebra, I think, is these operations of evaluation, right? Like in order to express evaluation algebraically, not just to presume that you have evaluation, but to actually have an algebra in which evaluation is an element, right? So that the evaluation is as you were suggesting here, is at least in part connected with the multiplication by the pseudoscalar. You need to be able to perform this contraction.
Well, that's right. That's how it's done. But I just might say that after you look at G11, the next algebra is G22, and that corresponds to the Dirac matrices and these ideas. So once you understand G11 relationship to just 2x2 matrices and G22 as relationships to the Dirac matrices, everything else is just notational. So that and of course the physics really comes in with the Dirac algebra and the Pauli algebra. Very important physics are done in just those two Clifford algebras, or space-time algebras, as Hesnes called it.
But what's always missing for me in the Clifford algebra is this differentiation, right? I mean, that we need this thing, the relationship between vectors as linear differential operators,
Okay.
and covectors as being the evaluation of the operators, right? So the covectors play the part of sort of integration, right? Whereas vectors play the part of differentiation.
Okay, so in Clifford algebra, you have the directional derivative corresponds to vectors, and gradient operator. Let's see. Yeah, so a directional derivative is the same thing as a partial derivative. So that corresponds to vectors then.
Yes. But for integration, we need formulas, covectors.
Yeah. Yeah, I can only get, yeah, I don't know what to say. I struggle with this idea of, where you're interpreting a directional derivative as a vector, really, and a covector. Yeah, that's a vector. A covector is then the dual of that.
Yeah, it's the operator that takes a vector back into the scalars.
Yeah, that's right. Like the gradient operator takes a scalar into a vector.
So in other words, it's like integrating a derivative.
Yeah, exactly. Well, that's right. So differential geometry, of course, can be very confusing because of whether you do it in Clifford algebra is quite different than if you do it in differential forms. You have to get used to the conversion formulas.
But if you could somehow establish a connection between the duality that you were talking about with these Grassmann algebras, if that duality was the same type of duality as we find between vectors as operators and covectors as operators.
Okay, well, I can see
That
what you're
would be
saying.
remarkable.
A more direct relationship. There are relationships that people know, of course, but you want more direct one, I guess. Like I say, a contraction of a differential K form is a K minus 1 form, but they're both they're both really covectors in the covector space.
But you can tell which one they're from if you do this decomposition, right? You can, so it's the A's and B's that are that. Yeah. So if A's are vectors and B's are covectors.
Oh, maybe I've lost you.
Oh,
Yes.
Are you still there?
Yes, if in this relation one can think in vectors and covectors, I think that all is in the same way. But I was remember that in Frolinger Nijenhuis algebra, they find different properties between multivectors and multiforms.
Yes.
And this can be very interesting to see how this is reflected in Clifford algebra, for example.
Yes, so it would mean that somehow the properties of these two Grassmann algebras that
Yeah.
Garrett is talking about, somehow they have to be a little bit different from each other. So right now, the relationship between the two Grassmann algebras seems completely symmetrical, but that doesn't quite match the properties of the vectors versus covectors, which
Yeah, that's right.
they
We're putting
do
them in
have
the same
different properties.
space as the problem. What we're doing and putting it in the same space. But the thing is, in the other language, they never even define a Clifford algebra. It's not defined. It's completely outside the definition of a vector and a covector. But I think Ojevich did write a paper about one of his early papers about that idea. I can't remember what the paper was.
Yes, there are some that he wrote. But this relation between vectors and covectors are I think that we can work in this following the ideas of Frolinger Nijenko's theory. Because here they find different kinds of relations, and then in Grassmann algebra, now we have not going inside the properties of A and B. I don't know if those are the same property, because I like it to think in A like a module, and the concept of module here in Grassmann, here in Clifford algebra, I don't know how can be used, and B can be the comodule, and then this is the base for the two different properties of these objects. Then I think that it is interesting. It could be interesting to see about these properties here.
Okay, yes, I think you're right. I think it's interesting.
Okay, well, maybe we should say we're gone as far as we can today. We haven't really decided quite what we would discuss in our next meeting, but I think it's reasonable to assume that we'll continue every 2 weeks unless you have any conflicts. If you agree to meet again in 2 weeks, then let's discuss perhaps by email what we should do in 2 weeks' time. I'm not myself quite ready to commit yet to doing something new. I'm not sure. Garrett, did you have something that you said you were working on that you'd like to present?
I could do something with, like, talk about what is called an enveloping algebra of a Clifford, of the simplest cases. I only consider 2 cases. I will also talk about the second case. Maybe I'll just put it on chat here for a second. So in other words, so we'll have G2 here. So that's the next case where A1 and A2 are anti-commutative and B1 and B2 are anti-commutative. So this is where we're generating matrices of 4x4 matrices. That generates the Dirac matrices, real Dirac matrices. Well, well, anyway, I can talk a little bit about it, but I'd like to talk about this idea of an enveloping algebra to see how you can even go to more general algebras that are more general than matrix algebras. So all we're really talking about, what I've written down there in that note there, G2 and G2 star, are just equivalent to real 4x4 matrices. So I can explain that, and then I can generalize that idea and not use nilpotents, not use A1 and A2, but any vector. Well, anyway, I'd like to talk a little bit about that. I think it would be interesting. That's what I'm thinking about now, actually. But
Yeah,
just, I'll keep it simple. Keep things simple.
I think that's very interesting to me. I mean, it does continue the theme that we have of duality. So
Yeah, maybe we can do something more along the lines that Jesus is suggesting. I think is very interesting too, to find a more direct correspondence of duality rather than the usual ways of looking at it.
but, okay, well that would be great. You know, if you could, you know, give a short presentation or a couple of slides or a few slides on this subject of an enveloping algebra, I think that would be
Yeah, that's
really
an
good.
important idea, actually. I've just learned about it myself, so exploring it myself, actually.
Okay, well, that's definitely the purpose of our seminar. So I would
So,
I would look forward to that then. And we'll see you in 2 weeks' time then.
okay.
Okay,
Okay.
Jesus?
Okay.
Okay. I enjoyed it again today. Because I have so much trouble with these computers. Anyway,
Well, you're coping quite well, I think. But internet,
okay.
it's worthwhile investing in a high-speed internet these days.
Okay, I'm gonna have to do better. I've got to do something. Okay.
Okay,
Okay.
see
Thanks.
you in 2 weeks.
Yeah, take
Bye
care.
for
Have
now.
a good week. Couple of weeks.
You too.